Welcome to the introductory video of trigonometry. This is just going to be an introduction. I'm not going to be solving some problems, just showing you some of the ratios, etc., and the definitions. To get started, let's go ahead and take a look at the word trigonometry itself. It's comprised of three Greek words: tri, meaning three; gon or gono, which is short for angles; and metry means to measure. Okay? And the Greeks, as well as others, did this in the context of astronomy. They'd take a look at a celestial body that was above the horizon, and they would create a perpendicular and a reference angle. And that reference angle, I'll go ahead and call it theta, with just a Greek letter. Theta looks like this. You're going to see this fairly common. And my reference angle is the angle of elevation as I look up toward the object. And what we have here is a 90 degree, so these two acute angles also add up to 90. So this is my reference angle, and this is the complement of the reference angle. This leads us to some very powerful mathematical studies. And to start off with, let's go ahead and take a look at, again, the reference angle. Now let me get this going here. What we have is when we elevate our angle of elevation, and I'm looking at some object up here, I have the ability to start measuring things. Now, first thing I'm going to do is go ahead and drop a perpendicular. And there's my right triangle. And my GT students who've already studied circles last semester will recognize this as part of the equation of the circle based upon the Pythagorean. So my reference angle theta, which could be of any degrees, gives me a relationship between this side and this side. This initial side, I'm going to take part of that initial side right here, and my terminal side, which is also my radius of the circle, and then this altitude, which is going to be a partial chord. The full chord, of course, will go all the way down, but we're just going to look at this partial chord and this partial chord right here. And that's going to have very specific relationships. We already done some of this. It wasn't recognized as such, but we did this in the context of some special right triangles. And the special right triangles work because of angle-angle similarity. If you remember, angle-angle similarity is whenever you have two angles that are congruent, the polygon itself is similar. Similar polygons are polygons where the angles are congruent and the sides are proportional. That proportionality is what makes trig, special rights, everything else work. Let's take a look again of our angle theta right here. And we're going to call this the same angle. Whether it's 20, 30, 35, whatever. Doesn't matter. That and that is the same. So we have this angle the same, the 90 degrees the same. Angle-angle similarity means these two triangles are the same. So I can set up proportional statements. And I can do x over y, and call that x1, y1 if you want, is equal to x1 over y1. So whatever these lengths are, when I come up with a proportion and a fraction, it's going to be the same simplified fraction, or simplified ratio. Let's illustrate this with a 3, 4, 5 triangle. I'm going to have a scale factor because similarity is nothing but, dilations and scale factor. I'll go ahead and make this a scale factor of 2, so that's going to be 6, 8, and 10. So when I do x over y, I'm going to have 3/4. And here I'm going to have 6/8, which of course is 3/4 or 0.75, okay? Now, I have 6 ways to do ratios. I can do y over r, I can do x over r, I could do y over x. There's many different ways. We're going to particularly look at 3 initial ways to set up these ratios and compare them. So, for instance, if I did y over r, 4 over 5, it's going to be the same ratio as this when we have 4 over 5 or 0.8. Okay? Now we're going to be dealing with a lot of decimals. This 0.8 represents the ratio. So when I say a function of something that's 0.8, I'm talking about a ratio of numbers, not the side length itself. The side length we can determine based upon what kind of dilation we have on the circle. Real quick, let's take a look at some special rights. Now, we did 30, 60, 90s, and what we did was a radical 3 in 2 ways. So over here is going to be a, which is 1/2, and a radical 3, which is going to be radical 3 over 2. All right? And the scale factor I'm multiplying by 2 here, so this is just going to be 1, and this is going to be radical 3. And I multiplied the scale factor by 4, the scale factor is 4, so this is just going to be 2, and this is going to be 2 radical 3. Now when we take these ratios, and I'm not going to work them all out because time reasons, and I have angle theta, and I do the opposite over hypotenuse, this is going to be my opposite, and this is going to be my hypotenuse. This is in relation to my reference angle. This being my angle that I'm going to be talking about, the 30 degrees my reference, not the 60 degrees. I'm going to just look at the 30 degrees as my reference angle. So I'm going to do opposite over hypotenuse. 1/2 over 1, that is. Okay, 1/2 over 1, which of course is equal to 1/2. Well, guess what? That's going to be 1/2, and that's going to be 1/2. They're all going to be the same. When I do adjacent, I'm talking adjacent to the reference angle, not the hypotenuse, which also has shared vertex of the reference angle. I'm talking about this angle right here, the adjacent. So when I do adjacent, radical 3 over 2 over 1, of course that's just going to be radical 3 over 2. And guess what? Radical 3 over 2, and when I simplify that, that's also going to be radical 3 over 2. It shares the same ratio. When I do opposite over adjacent, that's 1/2 over radical 3 over 1 over 2. And when I simplify that, I'm going to get radical 3 over 3. Remember, we don't have radicals in the denominator. So when I do 2 over 2 radical 3, that's just 1 over radical 3. We simplify it. All right? So all these will be the same. We're not always going to deal with 30, 60, 90s or 45, 45 special right triangles. We're going to deal with all the angles that can possibly happen between 0 and 90 degrees. So let's take a look at this. This is where we come up with our sine, cosine, and tangent. Now these words are derived out of Latin, which have precursors from Greek and even Sanskrit. Sine is just basically derived from the arch of a bow, basically. Cosine actually literally means the complement of the sine. Now, when we talk about sine, cosine, and tangent, we're always talking in relationship to a reference angle. It's either going to be one of these two acute angles, this one or this one up here. Since that one's theta, I could call this one beta if I wanted to. All right. And they have very special relationships on how we do the ratios. Here's a good illustration of it. So I have here the sine. It is defined by the reference angle opposite over hypotenuse. Opposite my theta, opposite my reference angle over hypotenuse. Now this is a function. You need to think of it like a function, f of x. My angle is my independent variable. That is a crucial understanding. We don't take the sine of anything but essentially an angle. And it's going to be one of my two acute angles. We don't do the sine of the 90-degree angle. It's these reference angles right here. It's either this one or this one. Now, if I decided to go up and change my reference angle to this angle over here, this now becomes adjacent and this now becomes opposite. My hypotenuse will always stay the same, which of course is opposite to 90 degrees. So we have opposite over adjacent. The cosine, which is the complement of the sine, is adjacent over hypotenuse, and the tangent is opposite over adjacent. Now my GT is already familiar with tangent. They worked with it before, but tangent just simply means to touch. And in context of a circle, well, that's not a very good circle. It comes along and just touches at one single spot. All right, and we're going to see how that can relate to a triangle here shortly. Now, all these trig ratios come down to decimals. When we saw basically 30-degree special right, when we did opposite over hypotenuse, it turned out to be 1/2. That's 0.5. Now, if I have 30 degrees right here, guess what I have? 0.5. Okay? And my trig looked kind of strange. When I did the cosine, it was radical 3 over 2. When I put radical 3 over 2 in the calculator, I'm going to get approximately that right there. And when I do radical 3 over 3 in the calculator, I'm going to get that as a decimal. All right? So our trig tables will vary come in decimals. When this guy did it, back over 2,000 years ago. He's the father of trigonometry. He actually did it in something called radians, or something related to radians. And we're going to explore that possibly next week. But right now we're just going to stick with these decimals. Here's an example. What I have here is a very basic triangle. Now we're dealing with 20 degrees, obviously not a special triangle. And I've rounded all my sides to whole numbers, 14, 5, and 15. So when we go and take the sine, which is opposite over hypotenuse, we should get a ratio of this side over hypotenuse to come out to be 34/20. But take a look what happens when I put it in the calculator. I'm going to do 5 divided by 15, which of course is 1/3, 0.3333. This is an example of a broken triangle. This triangle is actually mathematically incorrect. There is a rounding error, and I'm showing you this to illustrate the seriousness of rounding in trig and in mathematics. If we do the cosine, 14 over 15, we should get 0.9397, but that wouldn't be the case if I put it in the calculator. So moving on, let's go ahead and round to the nearest tenth. So what I have here now, let's just take a look at the sine. When I put 5.1 in the calculator, divided by, let's get that calculator up here. It's not doing it. And it's frozen. Okay, well, not going to happen on the calculator. Why? I have no idea. There it goes. Okay, so I'm going to do 5.1 divided by 14.9. And I'm not going to show you all these because of time reasons. I get 0.3422. Getting awfully close. So, and if I were to do the cosine, I'll get awfully close to there too. I would just do 14 divided by 14.9. Now, here we're rounded to the nearest hundredths. So I'm going to take 0.14, oops, that was cosine. So 5.1 divided by 14.92 will give me 0.3418. Much closer this time. And of course, when I go to the thousandths place, or a little bit further out, I'm going to have, watch this. I'm doing just sine. 04 divided by 14.923, and I'm finally getting there. All right, it's still a rounded answer, but now we're starting to get a good degree of accuracy. And if I were to put the other ones in there, if I were to do the cosine, which is adjacent over hypotenuse, so 14.023 over 14.923, that'll come out in the calculator. And the same for tangent, which is opposite over adjacent. 5.104 divided by 14.023 will give me that number right there. So these are trig tables, and this is what I used in college because we weren't allowed to use calculators in college. Very, very cool stuff. And as I said, I'm not going to be solving problems. That'll be in the next video, but I wanted to illustrate this. Now, what we have here is a radius of 1. That's pretty important because we are starting with 1 and we'll have scale factors. When I divide opposite over hypotenuse, I'm dividing by 1, so this length is actually my cosine. This length is actually my sine. But when I have a scale factor, when I do my trig ratio, it boils it down to one of these basic numbers right here on this table. So this does not reflect, this does not reflect the side length, it reflects the ratio. So we're going to be solving triangles in the next video with scale factors and side lengths bigger than 1. My GT class may recognize this as delta y and delta x. Basically, this is my x coordinate. That's going to be my y coordinate. And here, I like this one because it illustrates what the tangent is in relationship to this triangle. This is related to our cosine. This is related to our sine. This here is my tangent. As we saw in last semester, tangent is to touch. Some places illustrate the tangent like this, coming straight up and down, and they extend this triangle up and bring it down. So it's touching at the x-axis right here, or it's touching at the hypotenuse and coming down to the axis right here. And next week and the following weeks for my GT class, we're going to, in addition to look at the cosine and the sine, so again, this is my cosine right here, and this is my sine relationship for unit circle 1, that is. We're going to take a look not only with the tangent, but the cotangent, cosecant, and secant. So that's what's coming up for you. Alrighty, so that is it for this video, a little over 15 minutes long. Remember, I'm going to have a couple more videos out for problem solving. Trig is a very, very powerful part of mathematics. It's one of our bridge mathematics. You had elementary where you did numbers, then you had algebra and started working with functions. That opened up a whole new world. Then we did Euclidean geometry last semester, and then that was just mathematics with shapes. That opened up an even more world. Trig is going to open up another mathematical world for you, and you're going to see that start to come in fruition in pre-cal and your calculus courses. Alrighty, I'm going to go ahead and get this posted.